A very interesting case that we are bringing from Georgetown and still in very close relation with the family, actually very good friends of mine. And here we are going to need a help from Dr. Siegel, hopefully to enlighten the audience and even myself. So here we have a 64 years old male diagnosed with IGG Kappa myeloma in 2020. His fish showed a translocation 414 and he had a 1Q amplification. He received triple therapy, induction consolidation, achieving a very good partial response, and then this was followed by high-dose chemotherapy and auto stem cell rescue in December 2020. Subsequently, he received maintenance with Revlimid, Isazomib, remaining in CR until May 2023. He relapsed and his disease was addressed with Data-BD in December 2024. Given persistent pancytopenia, he had a bone marrow which showed 50% cellularity, trilineage dysplasia, abandoned ring sideroblast. The blast count was 3 to 5%, CD34 117 positive, and CD56 plasma cell clonality restricted 5%. So I want to deliver this information to Dr. Maher Alvitar for the genomics.
So we had, so this is actually, as you can really see, patient has germline abnormalities in mute YH and SAMD9, which are not relevant, but at the same time had these mutation in TP53, AGFR4, MGA, and read and SOS 12, but at the same time had this translocation, the 414 translocation, which actually, as you can really see here, with breakpoint, which I will discuss later, in addition to the translocation involving the 614. So it has multiple chromosomal abnormalities, as you can really see here, and the patient is clonal, as you can really see here for the Kappa. So in general, we always, when we get multiple myeloma samples, we sort the plasma cells using antibody for CD138, and we sequence the DNA and the RNA separately. Then the flow-through cells, we actually, these are the plasma cells and these are the flow-through cells, and we do exactly the same. We sequence DNA and RNA. So for all practical purposes, we do 4 sequences for each samples of multiple myelomas. Of course, we do actually the same thing for testing when we get peripheral blood. We isolate the cell-free DNA and the cell-free RNA, and we sequence the DNA completely different from the RNA. That gives us a lot of information to allow us to compare the plasma cell fraction versus the granulocyte fraction, as you can see here, alluded to as granulocyte versus the multiple myeloma fraction. So if we look at the chromosomal abnormalities in this particular patient, so here we can really see in the multiple myelomas, we can really see here the 5Q minus and the 6 plus and 13 minus. We see different abnormalities on the granulocytes, as you can really see here, to some extent different. Now, when we look at the mutation, so here I'm showing the DNA mutation in the multiple myeloma cells and in the granulocyte cells. And at the same time, the mutation as we see them in the RNA, detected by the RNA in the granulocyte, in the multiple myeloma cells and in the granulocyte. Now, there are mutations still, the MUT-YH and SAMD9. L, actually, they are germline detected in both at the same level, but at the same time, we see these mutations actually in TP53 that detected in the granulocyte as well as in the multiple myeloma fraction. And as you can really see it here, detected at a very high level in the granulocyte, as a matter of fact, higher than the level we see it in the multiple myeloma. Remember, this patient didn't really have 17B deletion, so it has a mutation in both allele, in both the granulocyte and in the multiple myeloma. And the mutations are identical. They are absolutely the same mutation in both. And we, as you can really see here, we detected these mutations using the RNA here as well as here. And there's actually some difference in terms of the level of percentage of a mutation in the multiple myeloma in the RNA as compared to the DNA. It is to some extent lower, which also suggests, the expression is different in multiple myeloma of TP53 as compared to the myeloid cells here. Now, if you look at the clonalities, as you can really see it here, we can see the clonality for the Kappa as well as for the heavy chains. You can really see here the level of expression of plasma cells is so high, 216,000 transcript for the heavy chains versus the second highest is only 392. And, this, how many levels of difference, just give you an idea, if you do the DNA clonalities, you are not going to see this difference, in terms of demonstrating clonality. And this is why I believe RNA for detecting clonality is significantly more sensitive than the DNA, especially in multiple myelomas. And simply because, as you all know, multiple myeloma, they are blue, the cytoplasm is blue because there are so much RNA in it, and that RNA is immunoglobulin. So definitely it is clonal for the heavy chain and the Kappa. And this is actually the fusion, as you see it, with the NSD2 genes, which is the same as the WHSC. This is the old nomenclature for NSD2. But the breakpoint here is actually, it's as you can see it here, the breakpoint, which is in the middle of the gene. Based on recent paper, in 414 translocation, dependent on where the break point, it will make a difference in terms of outcome. And the worst outcome is when the break point is in the middle of the NSD2 genes, which is called late interruptions. But let's look at the expression levels here. So as you can see, the granulocyte here, we see increase in CD34. This is the multiple myeloma cells. There's no CD34 here. And if we look actually at the KIT, actually is high here in the myeloid cells. KIT is CD117. And if we look at the multiple myeloma marker, CD138, it is in the multiple myeloma fractions, and it is not seen as well as BCMA, and it is not seen in the myeloid fractions. Now, hopefully this, why it is doing this? There are more slides actually.
Do you want me to ask you a few questions?
Yeah, go ahead. Yeah. So the bottom line, here is that this is a prime example of this case where it is stem cell disease and the same cells with the same mutation differentiating into the multiple myeloma as well into the myeloid disease. So here we have very aggressive MDS disease that carries exactly the same mutation we are seeing in the multiple myelomas.